Alrighty, everyone. Well, welcome to our first Meet the Astronomer here virtually at Vanderbilt Dyer Observatory. So this is our first Meet the Astronomer for this February. I'm Dr. Billy Teets, and I'm the director here at the Vanderbilt University Dyer Observatory. And I'm delighted to have all of you with us here. Can't wait for us to be able to have everyone back up at the observatory, but I'm glad that we're still able to connect with everyone, at least virtually. So we've got a great program tonight. So we're going to have Dr. Maria Charisi speaking to us about gravitational waves and black holes and all of this really interesting stuff. So before we get to that, though, I did want to give just a few little announcements about some things that we have coming up here at the Dyer Observatory, at least virtually. So this February 20th, which is on a Saturday, starting at 6:30 and going for about 2 hours, so 6:30 to 8:30 Central Time, we will be joining Warner State Park or Warner Park Nature Center, excuse me, and a few other members around the Tennessee area, including the Barnard Seaford Astronomical Society, Memphis Astronomical Society, and the Bays Mountain Park and Planetarium to do our second Tennessee Virtual Star Party. These are a little bit different, just a little bit from what we've been doing over the past few months. Our first Virtual Star Party, we teamed up with Warner Park and our collaborators to have the first Tennessee Virtual Star Party back in the middle of 2020. It's hard to believe that that much time has already passed now. So I hope you can join us for that. That is going to be a free event, and details can be found on our homepage, dyer.vanderbilt.edu. We've also got, not 1 week, but 2 weeks from now, we have another gravitational waves lecture that's going to be given by Dr. Stephen Taylor of Vanderbilt University. So he and Dr. Charisi work together. So we're going to get a double dose of gravitational waves, which you can't get enough gravity or gravitational waves. Let me just put it that way. There's always something incredibly interesting in every single talk, something new that we learn every time. So I'm excited for tonight's talk. I'm excited for the talk in 2 weeks as well. So hope you can join us for that one as well. We've also got on our homepage, one of our colleagues, well, practically Dr. Alex Rockefeller, has put together this phenomenal calendar of events for February. So it's our celestial calendar. It features a wealth of information of all different topics. So you can download that for free in a PDF or an image format, and you can print it off at home, but there's lots of info on there, so I highly recommend that you check it out. So again, all of these events and the calendar, you can find that information on our homepage, dyer.vanderbilt.edu. So today is a special day because we've got Dr. Charisi talking. Today marks the 6th anniversary of the first public announcement that gravitational waves were detected, which was truly mind-blowing. I was sitting in the audience watching a live stream of that. So it was incredible to be able to experience, hearing that announcement for the very first time. We also have, as we saw on our home screen, today is International Women and Girls in Science Day. So we're celebrating that. I'm very happy that Dr. Charisi could join us tonight. And also, very close, it's a very important day for us here at Dyer Observatory because it also happens to be the birthday of Dr. Carl Seifert, who was really kind of like the father of Dyer Observatory. So if Dr. Seifert was still with us today, then he'd be 110 years young. So happy birthday, Dr. Seifert. But without further ado, let's get to the star of tonight's program. So Dr. Maria Charisi is a black hole astrophysicist at Vanderbilt University. Her research focuses on electromagnetic and gravitational wave observations of supermassive black holes. Maria got her bachelor's in science in physics from Aristotle University in Thessaloniki in Greece, and her PhD in astronomy at Columbia University. Subsequently, she was a postdoctoral fellow of the North American Nanohertz Observatory for Gravitational Waves at Caltech. And in the past October, she joined Vanderbilt with a postdoctoral fellowship from the Vanderbilt Initiative for Data-Intensive Astrophysics. So, Dr. Charisi, thank you so much for joining us tonight. We are delighted to have you. And from what I'm told, it looks like it's daytime right where you are, but you're actually over in Greece right now, and it's 2 a.m. Is that correct?
That's correct.
All right, let me stop my screen share and turn it over to you. Thank you so much again for joining us.
Thank you, Billy. Let me share my screen. Okay, does it look okay? Okay. Okay, thank you for the introduction. I'm very happy to be celebrating with all of you the International Day for Women and Girls in Science. As a woman in science myself, this is a very important day. I'm also happy because, as Billy already said, it's been 5 years since this monumental announcement, this historic paper that reported the first detection of gravitational waves from merging black holes. Before I dive into gravitational waves and black holes, I would like just to spend a few minutes to talk about my path in this field and how I got interested in black holes and ended up doing research at Vanderbilt. So as Billy said, I am originally from Greece. I grew up in a small town in central Greece. And in high school, I was fortunate enough to have a great physics teacher that inspired me to study physics. So I moved from Pili, my hometown, to Thessaloniki and studied physics in the Aristotle University. And towards in my senior year, when I had decided that I wanted to do research in physics, but I wasn't sure in what exactly, I went to one of the public nights at the observatory there, and I heard the talk about black holes and gravitational waves, the LIGO experiment, and the upcoming then detections of gravitational waves. And it kind of blew my mind, and I decided that I myself wanted to become a gravitational wave astrophysicist. Once I got my bachelor's degree in physics, I moved to New York to get my PhD in astronomy. And towards the end of my PhD, exactly 5 years ago, the LIGO collaboration announced this tremendous discovery of gravitational waves. So after I got my PhD, I moved to Los Angeles and joined Caltech with a postdoctoral fellowship. And 1 month after I moved to Caltech, these two gentlemen here, who are among the fathers of the LIGO experiment, got the Nobel Prize for the first detection of gravitational waves. And since October, I moved to Nashville. And unfortunately, because of the pandemic, we are all stuck at home and spending our days mostly in front of a computer and talking to people through Zoom. Okay, enough about me. Let's start about our story about gravitational waves. Several years ago, Newton in 1687, he was also stuck home due to a pandemic, and he was thinking about gravity. So he came up with a theory that could explain how an apple falls onto the ground, how the planets move around the sun, and so on. This is probably a theory that most of you have heard at school. The idea is that every object that has a mass pulls gravitationally every other object that also has a mass. And the force, the gravitational force, is proportional to the mass and inversely proportional to the distance. So the apple falls because it feels the gravitational pull from the Earth. The moon moves around the Earth because it also feels the gravitational pull of the Earth, and so on. By the beginning of the 20th century, we already knew that even though the Newtonian theory of gravity is exceptional for everyday applications, there are instances that the theory breaks down. For example, if we look at Mercury, which is the closest planet to the sun, the orbit deviates slightly from what Newton predicted. So we knew that the Newtonian theory of gravity had its limitation. So Einstein came along and he came up with a new theory of gravity, which is called general relativity. And in that theory, the space and time are one thing called space-time. Every object that has a mass curves the space-time, and other objects move in that curvature. And that is what defines how the objects move in space. This can explain how the moon moves around the Earth. The Earth makes a dent into the space-time and dictates how the moon orbits. And then the sun makes an even bigger dent in space-time and defines how the Earth revolves around it. Another prediction of the theory of general relativity is gravitational waves. The same way that we drop a pebble into a calm surface of a lake, and we have ripples propagating outwards. When we have moving masses in general theory of relativity, they also create waves. They create tiny ripples in the fabric of space-time itself, which also propagate outwards with the speed of light. Actually, Einstein came up with this idea about a year after he came up with relativity, but then he thought he made a huge mistake, and he was actually trying to retract the article, but the journal didn't let him, fortunately. So what happens when a gravitational wave passes through an object? Let's say we have a gravitational wave that comes towards my direction. And what happens is it stretches and squeezes space-time. So if the gravitational wave is coming this way, I will become taller and thinner, and then shorter and fatter, taller and thinner, and so on in a periodic manner. So I want to emphasize the two things here. One is that throughout the talk, I already used it in the title, I will use this analogy of sound. So you will hear me saying, we heard the universe for the first time, the sound of the universe, black hole symphony, and so on. I just want to emphasize that this is an analogy. We don't have air sound waves. We don't have compression of air. After all, in space, space is almost pretty much empty. The second reason, but the reason we use it is because everything we knew so far was from photons, from things we can see. But it's the first time that we can observe the universe in a completely different way with gravity. So it's as if we unlock another sense. And the other reason we use a lot this analogy with the sound is the frequencies we can detect from ground-based detectors. They are very similar to the frequencies that we can hear. So practically we can translate a gravitational wave signal to a sound wave. The second thing that you should keep in mind is that gravity is very weak. I said that things that move around create gravitational waves. I'm moving my hands around, I'm creating gravitational waves, but there is no way you will see me change in shape and form because of the gravitational waves, because these are very weak. And you already have the experience that gravity is weak because you can stand up. Like the strength of your muscle can counteract the gravitational pull from the entire Earth. So in order to have any chance of detecting gravitational waves, we need very massive objects that move very, very fast. And fortunately, nature has been generous about this. And we have this kind of objects. They're called neutron stars and black holes. These are the end product of stellar evolution. So big stars, when they exhaust their fuel, they end up their lives either as neutron stars or black holes. And just to give you an idea of how dense these things are, here I'm showing a map of Nashville. And if I take the entire sun and compress it to something like the size of Nashville, the city of Nashville, we get a neutron star. If I further compress it down to something that would fit something like between downtown and the Parthenon, then I can make a black hole. So the entire sun, I squeeze it to a very small area, and I make this most dense object in the universe. So for example, if we squeeze the Earth, it could practically fit in a sphere that is similar to my fingernail. So you can imagine how dense this object is. It's so dense that not even light can escape. So if we have a pair of black holes and a pair of neutron stars, and we have a detector that is 1 meter long, when gravitational waves will be produced by this fastly rotating pair, the space-time will be squeezed and stretched by this amount. You can see this is a lot of zeros. This is 10 to the minus 21 meters. So this is a very, very, very tiny amount. We actually don't really comprehend these numbers. So if I make my detector 10 meters, this number will become 10 to the minus 20, 100 meters, 10 to the minus 19, I'm sorry, and so on. And just to give you an idea of how small these changes are, if I make a detector that has the size of our own galaxy, the change from the gravitational wave will be of the size of a basketball. Of course, as you can imagine, we cannot make a detector that is as big as the galaxy, at least for this type of experiment. So we're confined here on Earth, so the best we can make is something that is a few kilometers or a few miles long. So for this type of detectors, what we expect, we need to detect is 10 to the minus 18 meters. The change is 10 to the minus 18. And again, whenever I think about these numbers, they don't really mean much. So I want to give you another illustration to hopefully help. So what I'm showing here is a hydrogen atom, which has 1 proton and 1 electron. As you probably know, hydrogen atoms are very, very small. Atoms in general are very, very small. So the animation starts from something that is already 1 million smaller than the width of the human hair. And every time I will zoom in, it will be 10 times smaller. So we start with a 10 to the minus 10. We zoom in, we get to the nucleus, which is the proton. And then what we need to detect is 1,000th of that. This is extremely small. So that's one of the reasons when I first heard about this experiment, I was so mind blown. How can we detect something like that? Of course, you can imagine that if we have a ruler, that's not gonna work, because as the gravitational wave comes through and it squeezes and stretches the ruler, it also squeezes and stretches the marks of the ruler. Fortunately, however, we can use light and the specific property of light. So light travels with a constant speed, which doesn't change ever. So if the space-time is stretched and the light has to travel a longer distance, it will take a longer time to bounce off a mirror and come back. If the space-time is squeezed, then the light will have to travel a smaller distance, and the time to bounce off a mirror, let's say, it's smaller. So this is the basic principle that we use to detect gravitational waves. So we built an instrument called an interferometer, which is an L-shaped detector, and it has 2 arms that are 4 kilometers long. So what happens is we have a beam of light that is split into the 2 arms of the interferometer. It moves 4 kilometers down, bounces off a mirror, and it comes back to the original splitter. So if the distances of the arms are 4 kilometers exactly, the light travels exactly the same amount in both arms, and they cancel when they come back. However, when we have a gravitational wave squeezing and stretching the arms, one arm will become longer, the other one will become shorter, So the light will have to travel a different distance, and they won't cancel when they come back to the L. So we have a characteristic pattern that is happening here, and this is how we can detect gravitational waves. So this idea has been around for quite a while. The story is that in 1967, Professor Ray Wise of MIT, he was a young assistant professor there, and they asked him to teach a class on general relativity. And he said, I didn't know anything about general relativity, but I knew how to make instruments. He was an experimentalist. And he came up with ideas on how you can measure the predictions of general relativity. By the end of the class, they had built a prototype of this L-shaped detector, which is what I'm showing here. And you can see that this is a very complex instrument already, even though it was the prototype small that it could fit in a room. Moving forward, in the beginning, I think people thought he was crazy. It was impossible to measure something so small. But 20 years down the line, he had convinced several people, both at Caltech and MIT, that if we push the technology that we had available at the time, and we designed a 4-kilometer interferometer, we had some chances of detecting gravitational waves. So in 1989, they submitted a proposal for funding to the National Science Foundation, and they had this sketch right here, which shows the L-shaped detector. This was a successful proposal. They asked for 2 detectors, 2 identical detectors, placed as far as possible in the US. So they built 2 detectors, one in Hanford in Washington State and one in Livingston in Louisiana. So the reason they wanted 2 detectors, there are actually 2 reasons. One is pretty much the same reason we have 2 ears. So we have 2 ears so we can get a sense of where the sound is coming from. The second reason is they were trying to build such a sensitive detector that pretty much everything could disrupt it, like an earthquake at one of the sites or an airplane passing above, a thunderstorm, anything could disrupt this detector. And we didn't want to find spurious signals. But if we had something detected here and also something detected 3,000 kilometers away, the exact same thing, not something, then we could be more confident that we are detecting gravitational waves. So these detectors were already built by the early 2000s. You can see 2 pictures here of the 2 sites. This is where the beam splitting happens. The laser beam travels 4 kilometers down where there is a mirror and bounces back. And this is a very, like the laser travels in a vacuum. So LIGO, this experiment that is called LIGO, took data for the first time in the early 2000s, but they didn't find anything because the detector was not that sensitive at that time. But they persisted, they updated the detector, developed even better technology, more innovative solutions on how to detect gravitational waves. And exactly 5 years ago, they announced that they had succeeded. So I'll just play this video because when I first heard it, it was such a fantastic moment.
Ladies and gentlemen, we have detected gravitational waves. We did it.
So we did it. It was a really big time. And I chose to emphasize the we part in this sentence. I'm not a member of the LIGO scientific collaboration, but this is a really tremendous achievement for humankind. So we all did it. And also this project was heavily funded by the National Science Foundation. So it was practically funded from taxpayers' money. So if you're paying your taxes, you also contributed to the success of this project. So the people who are working in this collaboration, of course, it's a really big one. And here you can see the names of all these people that contributed, actually worked on the project. And it's a collaboration of more than 1,000 people. They are spread across the US and pretty much everywhere in the world, in Europe and Asia and Australia, so pretty much everywhere. And of course, there are people at Vanderbilt as well that contributed to this project. So what exactly did LIGO see? So the detector in Louisiana first, and then 7 milliseconds later, the detector in Washington saw practically the signal that I'm showing here. This is a waveform, we call it. And this GW150914, it stands for gravitational waves, that was detected in 2015, September 14. So this is pretty much the data with a very little cleaning. And that actually was a dream come true. Nobody was expecting that we could pick up with our eyes the signal. This is exactly what when we were simulating black holes in the computer, we were getting this signal right here. So I will play a computer simulation to illustrate what LIGO found. So here we have 2 black holes moving around, and you can see also the dent in the space-time that I was describing. As the black holes rotate around each other, they lose energy to gravitational waves, and they come closer and closer together, and they start moving faster and faster. So you can see that they complete an orbit faster and faster, and the strength of the gravitational wave signal goes up. At this point, we have the 2 black holes joining into one, and then this one rings down. It's initially deformed, and it becomes a nice spherical black hole. And then we have gravitational waves propagating outwards through the universe. And of course, they reach our detectors here on Earth, and we found this wavy form that we saw before. As I said, I will use a lot the sound analogy, and hopefully you can see that. You can hear it. I'm hoping that you can hear it. So this is what LIGO practically heard. So if I take the data, which is exactly what LIGO detected, and shift it by 200 hertz, which gets to the most sensitive frequency part of our ears, maybe you'll hear it a bit better. So you're hearing a chirp sound. The frequency goes up as the time passes, and I'll try to play it one more time. So I want to take a moment and describe the amazing facts about this first discovery. So this was, of course, the first direct detection of gravitational waves. This was also the first direct detection of black holes. We had a lot of indication by that time that black holes existed, but practically this was the first direct detection. We saw 2 very big black holes that had masses of about 30 times the mass of the sun. As I said, if you take one solar mass, it's something like the downtown Nashville area, the size. So if you take something 30 times that, and these 2 things rotate so fast that they complete 17 orbits within a second. So also this is a very energetic event. When they collide, they release a lot of energy in gravitational waves, and that energy is comparable to the amount of energy that all the stars in the universe release at that time. Also, it's a completely new way to observe the universe. The collision happened 1.3 billion years ago, and it traveled all the way through the universe to reach the Earth. And it turns out that we turned on the detector, and just a week later, we got this signal that was traveling for 1.3 billion years. And of course, all of these are a fantastic achievement for science and for astrophysics. But for me, it is also mind-blowing the technological achievement that we managed to build such a sensitive detector that we could measure something that is about 1/1000th of the size of a proton. So of course we knew that once we detect the first one, we won't stop there and we will keep looking. And of course, we were very happy to see many more black hole binaries. So here you see another 10 of those that were detected within the first 2 years of operation. And here is a compilation of the binaries that LIGO detected. So the blue ones, we have 2 black holes that combine, collide, and make a bigger black hole. The purple ones are the ones we already knew from electromagnetic observations. Just by seeing light from those sources, we could infer the presence of a black hole. So you can already see that we are finding not new types, but more massive black holes than the ones we know already. And some of them are extremely challenged to explain how they were formed. We typically think that black holes are formed when very massive stars collapse, but maybe we cannot produce these massive black holes. On the bottom here, I also have the other type of signals that LIGO can detect. With yellow, we have the single neutron stars that we knew before LIGO, and with purple, we have binary neutron stars that collided and either gave the most massive neutron star that has been ever detected or the least massive black hole. Either way, it's a very new and interesting thing that we are observing with LIGO for the first time. I won't discuss neutron star mergers much because this is a whole new topic and it could take me another hour, but I will say in the case of neutron stars, unlike black holes, we have matter around the neutron stars. And we expect, except of gravitational waves, we also expect electromagnetic waves. So we see the same event with 2 different ways. Of course, observing binary black holes with LIGO, it became a routine. We would have one at least every week. This is a calendar from January last year. So that was almost the last month before the pandemic. And then during the pandemic, they switched off the detector. And of course, the LIGO collaboration developed an app that you can download at your phone and you can get an alert every time a binary black hole is detected by LIGO once the detector is turned back on. So far I've been describing black holes of this stellar mass, the end products of stellar evolution. And I'm almost pretending that there are no other black holes out there, which is not true, because we know that there is at least one other type of black holes, the supermassive kind. These have masses of 1 million to 10 billion times the mass of the sun. And here I'm showing probably a picture that you have seen. This is a picture of a supermassive black hole in one of the most nearby galaxies. And we know that, like stars and people as well, galaxies like to live in pairs. So they very often collide and form bigger galaxies. And when that happens, because every galaxy has a supermassive black hole, the final galaxy will have 2 supermassive black holes, which will orbit around each other. And when they get too close together, they will emit gravitational waves. And we also expect that this happens very often. So even though we cannot detect those from the ground, this is a completely new set of gravitational waves that we could detect in the future. And if we learned something from the history of astronomy, astronomy started from observations in the optical light when Galileo pointed his telescope on the planets. But as we developed better technology and bigger telescopes, we managed to detect other windows of the electromagnetic spectrum. And we learned so much more about galaxies and the Big Bang and planets and so on. So we have been observing in gravitational waves for only 5 years, and we have already learned a lot. But you can imagine that we expect to learn much more as the time goes by and we observe more and more types of gravitational waves. So I will spend just a few minutes here to describe the other types of gravitational waves that we expect, those from supermassive black hole binaries that are produced when galaxies collide. One experiment is called LISA. It's the Laser Interferometer Space Antenna, and it pretty much uses the same idea as LIGO. We take an interferometer, we have laser beams, and we put it in space. And the advantage there is that we can, on the Earth, we are sort of confined at how far we can put the two arms. But in space, we can put them very far apart. And actually, the plan for this one is to put them at 5 million kilometers or so. So this will be a much more sensitive detector. It will detect some of the black hole binaries that LIGO detect, but it will also detect supermassive black holes. This is a partnership between NASA and the European Space Agency. It's currently planned and studied, and hopefully it will fly by 2034. The next experiment, which is actually close to heart because this is the type of things that I'm working on, it's called pulsar timing arrays. This one doesn't use interferometers, but it uses actually pulsars, which are neutron stars that are rotating. So neutron stars have a radiation beam, and as they rotate, when the beam crosses our line of sight, it produces a burst of radio waves. And if we have a radio telescope here on Earth, we can see these radio waves. And because the neutron star rotates very fast, we see them repeating very precisely. So what happens when we have a galaxy merger and the supermassive black hole binary is that they will emit gravitational waves that will propagate through the universe, and at some point they will reach our own galaxy. And they will start squeezing and stretching the space-time and the distance between the pulsar and the radio telescope on Earth. So that means that some of the pulses will have to travel a smaller distance and some of them will have to travel a longer distance. So some of the pulses will arrive faster and some of them will arrive later. And if we see that across multiple pulsars, we can detect gravitational waves. These are gravitational waves from the most massive supermassive black holes. These supermassive black holes have masses from 100 million to about 10 billion, the mass of the sun. Unfortunately, I won't have much time to go into more details here, but as Billy said in the beginning, if you're interested in that, there is a talk by Stephen Taylor in 2 weeks that will discuss the low frequency gravitational waves. And I want to just summarize with my, let's say, how I see astronomy now and how I used to see astronomy 5 years ago. So 5 years ago, we had a lot of information from light. We were collecting photons for several decades and more, and we had a pretty good understanding of what's happening in the universe. But I think now we have a lot more. I'm using again the analogy of the sound, but if we have an extra way to observe the universe, we can focus so much more. And of course, we can build a more complete understanding of what's happening in the universe. And with that, I would like to thank you for your attention, and I'm happy to take questions.
All right, well, thank you very much, Maria. That was really, really interesting. And I've said this about a lot of our talks. You know, I learn something new every time. Doesn't matter how many times I hear about gravitational waves. There's always something new that's, you know, fitting into that puzzle and just making everything, you know, make much more sense for me. So thank you for all of that. Do have some questions. So in one of the slides, it was where you had all of the different black hole mergers that were being detected, and you had the neutron star mergers as well. Some of those, they were labeled as EM black holes, which I think you said would mean that there was also light that was coming from those to help us detect their presence. Would you be able to elaborate on where the light was coming from?
Yeah, so as you can see, when the blue ones that are LIGO black holes, we have two of those that are merging and form a bigger one. The ones that are purple, they are single black holes. Mm-hmm. And what happens there is we have a lot of stuff around, gas around the black hole. And because we have this strong gravitational pull, the gas is moving very fast around the black hole, and there's also a lot of friction. So as a result, we can see X-rays. Sometimes we can also see radio waves. So we can see electromagnetic waves and just from the gas that is around the black hole. Mm-hmm. And actually, we don't really see the black hole, but we infer the presence just because it's the only thing that can produce this energy. That's why I said with black holes, it was the first direct detection of the black hole.
Okay. Let's see, actually staying on this slide, you have down at the bottom a couple of the LIGO Virgo neutron stars. So those are two neutron star mergers. Is that correct?
Mm-hmm. Yeah, so these are the two.
Okay, and were those were also observed in light as well? So once was it the gravitational waves were first detected, and then telescopes were on the ground and also in space were then pointed to where we thought the gravitational waves would be coming from, to where we could actually see the light from that merger as well?
Right. So this is exactly it. I think we were successful in observing both the gravitational wave and the electromagnetic signal only for one of them. Mm-hmm. So what happened was that LIGO saw the gravitational wave signal. It gave an alert to all the observatories in the world that have a collaboration with LIGO. About, I think it was 2 seconds or a fraction of the second, the Fermi Space Telescope saw a gamma ray burst from roughly the area that we saw the neutron star merger. And this is sort of the signal that we were expecting. Then we could, let's say, constrain the area in the sky that this gravitational wave signal came from. Mm-hmm. And then a lot of optical observatories pointed to different galaxies in that area and finally saw something that wasn't there, a flash in optical light. This is called the kilonova, and that lasted, they could see it for about a week, and then they could see lower energy counterpart. When the optical faded, they could see the radio, the infrared, and so on.
Okay, and if I'm remembering correctly, so the neutron stars are, as their name implies, are mostly neutrons. But when these merged, the electromagnetic signals, actual light that we saw from, which could tell us about what materials were produced in that, wasn't that where we were seeing a signal like there was a lot of gold and platinum in the spectrum? So it ended up, when you did the math, which each of these neutron stars is about something like 500,000 times the mass of the Earth, when they collided and merged, it ended up producing something, I forget how many Earth masses of pure gold and platinum. Is that correct?
Yeah, that's exactly it. We learned actually how these heavy elements are produced, and they produce a significant amount of gold and platinum. So yeah, we know how gold is formed now.
Gotcha. If a pair of merging black holes or a set of monitored pulsars were much closer to us, would the magnitude of the observed gravitational waves be greater, like some sort of like being closer to a sound speaker? If you're closer to the speaker, it sounds louder. Would the gravitational waves essentially be louder?
Yes, that's absolutely true. The closer gravitational wave source is, the stronger the signal, and also the more massive the gravitational wave source. So, for example, this binary here produced a stronger gravitational signal than these.
Okay. Do gravitational waves experience something analogous to redshift of light waves?
Oh, that's a good one. And I'm actually not sure, so I won't just risk saying something that I don't know.
No, that's fine. I mean, if we don't know, then that's something that, us at home could try to find out, and maybe that's one of the big questions still in gravitational wave astronomy. So
I would say probably someone knows the answer to that, but I'm not that person.
Okay. Do you know how much it costs to build LIGO?
Oh, I think the initial proposal was something for 250 million, but I think over the years it has been more than $1 billion.
Gotcha. Okay. Then we have one question here. Do you coordinate where you point your apparatus? In other words, let's see, or basically so that you can share and cooperate, and basically more than one person or one group use LIGO.
So LIGO is an all-sky detector. So we are not pointing the telescope somewhere. In order to have access at the initial data, I think you need to be part of the collaboration, but eventually they make their data public for everyone. I'm not sure I got, is that what the question was?
Yeah, I think so. I think maybe a little bit of a misconception that you steer or point the telescope, or if you want to call it a telescope, the observatory. But yeah, I mean, it's basically fastened to the ground, and it's essentially an omnidirectional telescope. Is that correct? So it can detect the waves whichever way they come in. Okay.
It is sensitive to some directions rather than some others, but this has to do with how it's built. But in general, we are not pointing the telescope. If there is a source coming from somewhere, LIGO will detect it.
Okay. Oh, and there was, so you showed us the two that were in the US, one up in Washington and one down in Louisiana. There's a third one as well. Is that correct?
There is one in Italy. It's called Virgo. And now they're more built outside of the US. So I think one of these sites had the twin, and they actually shipped that in India. And Japan is building a new gravitational wave observatory that will be underground. I think after the first detection, more and more countries got interested in this type of science, and more are trying to join this game.
All right. Let's see. I'm just trying to make sure we didn't miss anything here. So when you were showing the schematic or the animation of LISA, which was the space-based gravitational wave antenna, so you said that the actual spacing between the detectors, instead of being 4 kilometers this time, would be something on the order of several million kilometers. So I would assume that would mean that on Earth, in order to get, say, something like with LIGO, to get something, a signal from like the black holes that you first started observing, that was something like 10 to the minus 18th of meters. That was the sensitivity you needed. But since you have much longer distances between these, then you wouldn't have to be quite that sensitive in order to detect those same black holes. Is that correct?
Yeah, I think that's a fair point.
Okay.
What happens is you also don't have the same sources of noise. For example, on the ground, you may have an earthquake, but when you're following the Earth, you don't have this type of noise. So this is going to be a significantly more sensitive instrument. And also because you place the detector so far apart, you can also detect different frequencies of gravitational waves that we would never have any hope of detecting from the ground.
And would that essentially be because if they were like super, super long gravitational waves, then it's kind of like both of the LIGO observatories would be moving at the same time, and we wouldn't be able to detect that. But now that we've got this much longer spacing, we can see those bigger waves.
Yeah.
Okay. All right. Well, I'm just looking through here. I think that we actually got all of the questions. I'm not seeing any others come in. So again, I want to thank you from Dyer Observatory. We thoroughly enjoyed this. And if there are other questions for folks at home, please send those questions in to us. We've got a contact us link on the observatory website, and we can get those to Dr. Charisi and get those answered for you. So Dr. Charisi, thank you again so much for this excellent talk and joining us here on the International Day of Women and Girls in Science. That was a great way to celebrate that. Let's see. I also want to thank a few of my colleagues that have been helping out behind the scenes, Alex Rockefeller and Helen Morset, that work with me at the Dyer Observatory, and then also Brian Smokler of VU News and Communications. So thanks to them for helping us to do our program this evening. So with that, again, check out dyer.vanderbilt.edu for our upcoming for our upcoming virtual events, which we have one next Saturday, and not this coming Saturday, but week after this coming Saturday, and then also Dr. Stephen Taylor's talk on the 25th. So thank you all again for joining us tonight, and I hope you all have a great evening.